Okay everyone, welcome to another episode. Here what we're looking at today is the solutions to the homework assignment that was set in the previous video on the live stream for Year 12 Waves. Now if you haven't had a go at these questions yet, then probably best not to look at this video, but pop down to the description below. You'll find the questions there, a link to the questions there, try them and then come back and see how you got on. Okay, so disclaimers out of the way, let's get started. So as a wave passes through a certain medium, the particles vibrate through a distance of 5 centimeters parallel to the direction of the wave, as shown in the diagram below. In the diagram, the particle marked X vibrates through a distance of 5 centimeters. So AB equals 5 centimeters. Alright, so you notice that I've read the whole question. Make sure that I'm happy with everything that's going on there. I've got my highlighter going on. And let's see what we've got. So what kind of wave is this? So from the diagram we've got the direction of travel of the wave, and we've got the motion of the particle, and from the description here we've also got parallel to the direction of the wave. So if we've gone along and done our notes well, we should know that this is therefore a longitudinal wave, okay, because the direction of the disturbance that's actually creating the wave, the backwards and forwards motion, is parallel to the direction of travel of the wave. Now, what is the amplitude of the wave? A little bit more complicated, this one. Now, you wouldn't be expected to draw what I'm about to draw in the exam, but you should be able to think on it. It's only 1 mark, so not a huge deal with this. Let's see. We're going from A, starting at X, so particle mark X vibrates through a distance of 5 centimeters. So we start at position X, this appears to be the rest. We go to A and then back to B. So if we were to kind of imagine how we would draw that as a graph, grab my regular pen here. If I would start at X down here, so this is X, and we go to A, and then we'd have to go back through X, down to B, and then back up again. This point up here would be point A, and this point down here would have to be point B. And we happen to know that A and B are a distance apart from each other so going from A down to B is a distance of 5 centimeters. Okay, so basically what it's saying is the height of my wave graph is 5 centimeters. But we weren't being asked for that. It's a critical point there. We weren't being asked for what's the height of the wave. We were being asked for what's the amplitude of the wave. And the amplitude of the wave is from the rest position, X, out to your extreme point. Okay, so your furthest away point. So what's the distance from X out to B? Since that whole thing's 5, and this is nice and symmetrical here, then this is the amplitude is half of 5, which is 2.5. Now that seemed to take an awful lot of time to sort out, but in the exam you just look at it and go, okay, rest position X, A to B, back again. Okay, it's half that. Move on. Okay, 1 mark. No working out required in either of those. 2 marks in the bag. Okay, on we go to question 2. The wave pattern obtained with the rope is shown again below. The end of the rope makes 24 vibrations in 8 seconds. Calculate the frequency of the wave. So this is a stem of a question, it's part of a question here. So let's take a look. So the wave pattern obtained with the rope is shown here. The end of the rope makes a vibration of 24 vibrations in 8 seconds. So what we've got the number of vibrations. So n is the number of events. So n equals 24. The time is equal to 8. And then frequency is what we're being asked to calculate. So we have our list of things that we want. Strongly recommend you do this, even though this is all about waves. When you're in the exam, it won't be obvious necessarily what the question is about or what formula it wants you to take. So write down what you got, and that should tickle your memory. So hopefully this tickles your memory of the fact that F is equal to N over T. I'm on a keyboard here, so I'm using this slash as an over. It should be a fraction ideally, but it's a little bit faster for me to write. So F equals 24 divided by 8, so F equals 3. Okay, and it's 3 hertz, but we've already been given that, so there we go. 2 marks in this one because it's a pretty straightforward one. There's no rearrangement required, so 2 marks. And moving on to the next one. Okay, so the sound waves produced by a vibrating tuning fork can be studied using a microphone connected to an oscilloscope CRO as shown below. Now, the key thing that you need to understand about a CRO is that it's a fancy sounding name for something that shows you a graph. Okay, it just shows you a graph like that on a screen where the x-axis is always time and the y-axis is always displacement, or distance away from start position, whichever way you want to put it. Alright, that's what this is. It's just a graph. Okay, so this here thing here is just a graph. Okay, so let's see. The diagram below shows the waveform seen on the screen of the oscilloscope when the tuning fork is made to vibrate. Okay, and the time is equal to 0.01 seconds. I think the whole thing's meant to be 0.01 seconds here. It's not a particularly good cover. I'll just go and check that with my original that I've got lying about here. Yeah, it's not a good copy of that, but yeah, that whole thing's going to be 0.01 seconds. Otherwise, that would be horrible. So the speed of sound is 340 meters per second. Calculate the wavelength of the sound emitted by the tuning fork. You're advised to show clearly how you get your answer. Alright, so cool. Let's see what we got here. We've got 3 marks here and we're looking to find the wavelength. Now, that means that we're looking to find lambda. Okay, so I can get my symbol tool out here. I think it's that one. So lambda is, in this case, the unknown quantity. We've been given the speed v equals, get myself off, symbol. That's not very good. Try that again. Take a new line. So v equals 340. And then I've got a bit of stuff going on. I'm not quite sure what's happening here, but I've got a pretty good idea that I'm going to be looking to find f. Right, because I've been given v, I've been given lambda, it's almost certain that this is a v equals f lambda situation. So I need to be able to find f. Okie doke. So time of 0.01 seconds is going on here. So that's an interesting thing. So let's take a look out here. So we'll draw a little line off to the side. Okay, and the whole thing is 0.01 seconds. So how many waves do I actually have here? I go all the way up, all the way down, all the way back up. That's my first wave. All the way up, all the way down, and all the way up again. So I've got 2 full waves going on in there. So let's get rid of that. 2 full waves. So n equals 2 for 2 full waves, because I need to find frequency, and I know that I need to be able to do that. And t equals 0.01. So f, again, just like on our last question, f is going to equal n over t. This is a question of confidence. I know that I need to find f because I know that this is the only equation that I have for lambda. I've been given v, so that lends itself to it. So can I find f? And I can. So f equals 2 divided by 0.01. So f equals, that's 20 over 0.01, 200 over 1, so that's 200. Yeah, 200. 200 hertz. Okay, so we can now pop that back in here and we get 200. Okay, so now we're in the position that we have everything that we need, because we've got v equals f lambda as our equation. If I could click the right button, that would really help. Which gives me that lambda, therefore, has to equal, by rearrangement, v over f. Divide both sides by f, or use your triangle. So lambda is going to equal v, which is 340, divided by 200. So lambda is equal to 1.7 in this case. So lambda equals 1.7. I've used all the standard units, so that should be in meters. The question gives me the answer in meters, so 1.7. You've got a bit of work to do there for 3 marks, I think, but nothing we couldn't handle. 1.7. Watch out for the 2-step situation. Okay, on we go then. Question 4. A sound wave travels through the air. Describe carefully the motion of the air particles as the sound wave passes. Okay, so what we want to first of all say is that when we're talking about the movement of anything, really, we're talking about vibration. So you want the word vibrates in here. So the air particles are going to vibrate. And how are they going to vibrate? They're going to vibrate back and forth, or side to side, or something along those lines. The idea is it's a forward backwards kind of motion. Alright, and then we know that sound waves are longitudinal waves. They're one of our examples for longitudinal waves, so we should now be able to say that the direction of the wave, or the direction of the wave or the direction of wave travel is parallel to the disturbance. And that's it. Okay, so our air particles vibrate back and forwards in a direction that is parallel to the wave travel. 2 marks. Okay, we have a graph below now. Love graphs. So the graph below shows how the displacement of an air molecule changes with time. So just a single molecule, so we're looking at time on this axis, so I'm immediately getting a little bit suspicious that we're going to be looking for frequencies, or we're going to be doing some cool stuff there. Okay, so I'm going to get in the case for that time one there. Okay, mark on the graph the amplitude of the air molecule's motion. Oh, amplitude, right, that's straightforward enough. Is your distance from the rest position along here up to a maximum, or your distance from a rest position down to a minimum. So that's an amplitude. So any one of these lines that I'm drawing right now will work for a mark. You don't have to draw them all, just any one of them. Okay, explain why the displacement of air molecules is sometimes positive and at other times negative. Okay, well, all we have to say there is that we have to say that sometimes you're moving in opposite directions. Okay, that the molecules vibrate about a fixed point, so sometimes they're on one side of that fixed point, and then at other times they're on another side of that fixed point. It's only a single mark, so you can get away with a little bit of waffle here, but the key thing is that the displacement is measured from a fixed point. So sometimes you're on one side of it, and sometimes you're on the other side of it. And that's what we mean by positive and negative displacement. Okay, so nothing else on that time one. I was wrong to highlight that, but always good practice when you're looking at graphs. What's on the x-axis, what's important. Okay, number 5, a microphone is attached to a cathode ray oscilloscope. So just from earlier on, we're remembering that a cathode ray oscilloscope is essentially just a set of graphs. Okay, so this is my graph here, like a little axis along the middle, and it's got time on this axis, so time all along here, and displacement up the side. That's what's going on. Okay, so let's have a look. So microphone is attached to a cathode ray oscilloscope. A tuning fork is struck beside the microphone. The resulting waveform that is immediately seen is shown on the diagram below. Okay, so we go up, down, up, down, up. Okay, as you watch the waveform, what changes would you expect to notice? Explain the changes. Alright, so what's causing this? Now we're stuck and we're in an exam. We go, right, why is it doing this? And it's doing this because there's a sound wave hitting it. Okay, so sound's hitting it and going backwards, forwards, backwards, forwards, backwards, forwards. So what's going to happen to that backwards, forwards motion over time? And as time goes on, that backwards forwards motion will get less and less and less as the sound fades, as the energy goes away, because a tuning fork is not like a speaker where it's continually pumping stuff out. You hit it and then it goes away. So we're expecting that because the motion of our particle is going to get less and less, that our amplitude of motion should get less and less. It's a bit like question 1, that if the amplitude or if the movement gets less and less and less and less and less, then the amplitude of the wave is going to get less and less and less. Okay, so what we're expecting is observation, amplitude gradually gets less. Okay, now the question is why? And the sound is getting quieter. Is the answer there? Okay, so our sound gets less noisy, gets less loud, and as a result we get less amplitude. Remember, amplitude and loudness are related to each other. Frequency and pitch are related to each other. Okay, when we're talking about sound waves. Number 6, a second tuning fork is struck beside the microphone and the resulting waveform is shown below. What 2 things can you say about the note produced by the second tuning fork compared with the first? Right, so we need to be able to see these two together. So there's our second tuning fork, and there's our first. Second, first, second, first. Okay, so what's going on here? Well, first thing is we can see the amplitude is greater. Okay, now we're talking about the note. This is a beauty. Okay, this is a beautiful example here. We are not talking about the graphs, and everybody here, well, not everybody, but the vast majority of average students start saying the graph has a greater amplitude, the graph has this, the graph has that. I don't care about the graph. I've not been asked about the graph, I've been asked about the note. So I know that the graph has a greater amplitude. What does that mean about the note? It means the second note is louder. Now if I was asked to explain that, I could say because it's got a larger amplitude, but it doesn't just say it, just says what 2 things can you say about it, about the note produced by the second tuning fork. It doesn't ask me to say and explain it. So the second note is definitely louder, we've got that. Alright, so pretty much the only differences you have in notes are loudness and pitch. So that's it. So what's the pitch like? The pitch is related to the frequency. So that would be how many waves I have in a given time. So in this one I've got, whoa, let's go crest to crest. So we've got one jump, two jumps. So we've got 1, 2, 3 crests, okay, and 2 troughs in this one. What have we got here? We've got 1, 2, 3 crests and 2 troughs. Ooh, coincidence? I think not. I think not. I think this is the case of, right, we've got the same number of crests, we've got the same number of troughs, so they have the same pitch is what we want there. Okay, so number of peaks. So what we have here is that the second is louder, and that we've got the same pitch. And that's us for this one. Okay, everyone. Thank you so much for tuning in. Hopefully this was helpful to you. Again, if there's anything you didn't understand, pop a comment down below, and I will see you in the next one.